Okay, I'm very happy to be here. Thanks for inviting me to this conference. And actually, the topic of this talk is a little bit outside of the mainstream experimental linguistics theme of this conference. But I have two excuses for being here. First, in the original call for papers, computational modeling was mentioned as one of the possible areas addressed in this conference. And second, at the end of my presentation, I will mention a little psycholinguistic experiment that we did. So this research is done by a group of people from various Moscow institutions, and actually Anastasia Linnik is now based in Potsdam, Germany. Okay, what we are looking at is the phenomenon we call referential choice, which is a very familiar thing. When we want to mention a referent, we choose between several options, such as a full noun phrase, including a proper name, such as Peter, or a description, like the Tsar. And sometimes we have mixes, mixed proper names with elements of descriptions like Peter the Great, or alternately, we very often use reduced noun phrases such as third-person pronouns. So we look at this phenomenon from the perspective of choosing. Every time we have a reference in mind, we have to choose between the available options. This example comes from the corpus of text we're actually looking at, and by way of very simple illustration, there is a description there is a proper name, there is a pronoun, and there are also zeros which can be ignored in the case of English, but you can also take them into account as possible antecedents of independent referential elements. So the research question we are trying to address for a number of years is how referential choice is made. What are the governing forces that affect the speaker or writer when he or she is using a certain referential device? And we believe that this question is important for a number of reasons, because it's a very common cognitive operation that we perform all the time as we use language, and also because referential expressions constitute a lion's share of all information in natural language. And if you don't believe that that's the case, it's very easy to demonstrate with the help of a manipulation originally proposed by Douglas Biber. Like, if you look at this sentence, referential expressions are marked in green and all the rest in white. And if we remove all referential expressions, you get something like this. But if you keep the referential expressions, you get a little bit more in terms of information. And apparently, it's not a real text. You cannot make a full sense of this sequence of words, but you get from that a little bit more than from their other condition. There is a very complex classification of referential devices, and you can look at them at different levels of specification. In our project, we are primarily interested in the two uppermost levels of this classification. That is the choice between reduced and full referential devices, and then at the second hierarchical level, at the choice between proper names and descriptions within full referential devices. And in comparison, there is currently a very productive tradition in computational linguistics called referential expression generation, REG, or sometimes GRE, that pays most attention to varieties of descriptive noun phrases, often with various kinds of attributes, sometimes complex attributes. And this is an important task too, but it's kind of second-order task to understanding the upper levels of this hierarchy in our view. Okay, referential choice is dependent on many factors operating simultaneously, and there are several groups of such factors, such as the distance to the previous mentioned, the antecedent, and it can be measured in a number of different ways. And there is a group of factors associated with the antecedent itself, such as its role, and there are also properties of the referent per se, which are important, and so on and so forth. I will show you a longer list of factors in a minute. So there are factors associated with the discourse context and the factors associated with the referent as such, kind of independently of the current mention of the referent. In terms of theory, we operate with this kind of model in which there is a variety of factors belonging to two biggest groups, as I already mentioned. Does this mouse work? Okay, yeah. Yeah. So there are, but you don't see it anyway. I don't think so. Okay. Well, there are two big groups of factors affecting the reference status in the speaker's or writer's current working memory, and that in turn affects referential choice. If a referent is highly activated, you get a reduced device. If its activation is below a certain threshold, you get a fuller device. But you can also look at this kind of cross-cutting directly from the factors and their mapping on referential choice, and that's what we are mostly doing in our computational modeling studies. There is one important factor among the factors we are using, so-called rhetorical distance, which is actually the distance along the hierarchical discourse structure. And in the previous studies, it has been demonstrated that that's a powerful factor, which is probably the most powerful one. And in implementing this factor, we're using the so-called rhetorical structure theory, one of the theories of discourse structure developed by Mann and Thompson. We could use a different theory, but we choose this one because the corpus we are working on has been annotated specifically for rhetorical relations by a group of American computational linguists, and that's basically the reason why you use this particular corpus. So we are trying to implement this factor and see how important it is in actual language use. By way of one simple illustration, there is a rhetorical tree of a little piece of text, and for example, if you look at this pronoun she, you can go to the nearest antecedent here via the linear structure, and that would be 4 steps. So the linear distance would be 4, but the rhetorical structure, which is kind of hierarchical semantic structure of the text, the distance is just 1, and that's an important thing. Several technical observations. The corpus we are working on is called RefRet. It's a combination of the previously done RST discourse tree bank that I mentioned before, and our annotation that we added on top of that. And currently we are working on the subcorpus called RefRet 3 and are using a so-called MORA scheme, which is an annotation scheme that our group has developed. The corpus we are currently working on contains, well, it has these quantitative parameters, and particularly important is that it has about 1,800 anaphor antecedent pairs, or anaphors, and according to a statistician and a computer scientist that is in our team, this amount is enough for doing sensible statistical modeling. And here is the list of possible factors affecting referential choice. There is one large group with internal classification that are discourse context factors, and at the top of this list there are reference features factors. Some of the factors are computed automatically. For example, the so-called protagonism factor is computed via a certain computational procedure, but some other factors are extracted from our annotation. And referential form is the variable that is actually being explored, the factor predicted variable. We are using the MMAX2 program designed by a group of German computational linguists specifically for this kind of things. And the properties, just mentioned a couple of properties of the Mora scheme that differentiate it from other similar schemes is that we include a wide range of possible activation factors, such as many different values of the grammatical Rowan factor, and also we have annotation of complex groups. For example, groups of noun phrases connected by coordination, or even discontinuous groups serving as antecedents, as for example in this picture, where the noun phrase, the analysts, has actually 4 distinct antecedents that are used in conjunction. And it's not an easy thing to implement this kind of in an annotation scheme, and that's what we have managed to do in this Mora scheme. There are 2 main tasks for machine learning work that we are working with. There is a so-called two-way task, distinction between full noun phrases and pronouns, and a 3-way task, definite description versus proper name versus pronoun. And the success of the modeling experiments is assessed with the help of so-called accuracy measurement, which is the ratio of correct predictions to the overall number of instances. There is a number of machine learning algorithms used in this study, including logical algorithms and logistic regression, and also compositions of algorithms so-called boosting and bagging, which somehow work on top of the more elementary algorithms and are supposed to provide more stable and more replicable results. The basic results of machine learning studies on this corpus are like this for a 2-way task and for the 3-way task. Apparently we are getting much better results for the 2-way task. Now in the vicinity of 90%, which means that the algorithm is able to predict referential choice as well as a human writer 9 times out of 10, more or less. We are getting lower but also fairly good results for the 3-way task. And I'm not going to discuss the 3-way task in any detail anymore, but it's interesting that the set of factors we are using was actually not originally designed for this 3-way task, and the fact that we are getting fairly good results is an interesting finding that requires its own interpretation. Okay. From now on, I will be primarily interested in the 2-way choice between full and reduced noun phrases. The question that arises with this result that we have right now in the vicinity of 90% is it possible to get closer to the 100% accuracy. And it's possible that there is some theoretical limit to which a model can possibly get. And the reason is that, as is known from a number of previous studies, there are instances of non-categorical referential choice. That is, instances when I can use either Peter or he with approximately same success or acceptability or probability. And if we return for a minute to our cognitive model where referent activation is immediately responsible for referential choice, apparently this activation can vary between a minimal and a maximal values, and it's a graded variable. But at the linguistic plane, so to speak, you have to do a clear-cut choice between Peter and he. If referent activation is close to the extreme sides of the scale, the situation is relatively simple, but if activation is somewhere in the middle, you can go one way or the other. And there are instances that, as we already know, in which, as we already know, you can use either one and it would both be acceptable options. If that is true, then no model can possibly predict actual referential choice with 100% accuracy. Because when there are instances of more or less random choice, then you always have to accept the divergence between the actual referential choice in the original text and the predictions done by the computation model. But in order to verify this approach, we have tried to do a simple experiment on understanding what we think is non-categorical referential expressions. We have identified 9 texts in the corpus, in our corpus, in which the algorithms have diverged in their prediction from the original referential choice. And these 2 texts were offered to experiment participants in 2 varieties, one in the original form and the other in the altered form in accordance with the computation model's preference. In order to test the felicity of this kind of these 2 versions of the text, we were asking participants a number of questions. There were so-called control questions on the general plot of the texts, and there were also experimental questions testing the understanding of the referential expressions themselves. So what we got is that the correctness of answers to control questions was about 84%. There were always instances when people made mistakes and answered incorrectly. And interestingly, the rate of correctness of answers to proper names, which are supposedly fully informative and explicit, was exactly the same. As for the questions to pronouns, which were offered by the computational model but were not in the original text, the accuracy of questions was significantly lower, 75%, and that was due particularly to 2 questions out of 9, two texts out of 9. If we remove these 2 texts, then the accuracy of answers rises to 80%, which is pretty close to what we have for other conditions. So we can conclude from this preliminary experiment that in general the algorithm diverges from the original in those places where that is acceptable to human language users, 7 times out of 9. And as far as these 2 other instances are concerned, maybe these are errors of the model, and we're still trying to improve its prediction, and maybe we reach a stage where all 9 texts in this kind of picture would give the same satisfactory results. So to make some conclusions on the non-categorical referential choice, it appears that there are instances when referential choice allows more than one option, and more than one option is available to normal language users. And as we understood at a certain stage of this project, a proper model of referential choice must account for this property of human speakers. We cannot try to improve the prediction to 100%. That's theoretically impossible. And at this stage, our model generally conforms to this requirement, but not quite. We still have to improve it a little bit more. We have a number of other things that we plan to do in the future. For example, one of the algorithms called logistic regression is able to evaluate the certainty of prediction. And that property of that algorithm allows us to try to correlate that with the human's assessment of non-categorical referential choice. That is, hopefully, if the algorithm says that a certain referential expression is all right with a certainty 75%, that may correlate with the answers of human participants, of a group of human participants, if 75% of them decide that this referential option is proper at this particular point in the discourse. And our preliminary analysis of those 9 texts that we studied experimentally, that I told you about a minute ago, basically supports this approach, but we still need to do a little bit more to be more confident. We're also working on so-called cheap data modeling. The annotation of the corpus that we have been doing is very labor intensive. And we need, after we do all this work, we can compare what the quality of the computational model is going to be with having all this annotated information available and without it. Many of the, certainly not all, but many of the potential factors affecting referential choice can be extracted with some kind of approximation computationally. And if we can do without laborious annotation and get quantitatively comparable results, then that would be very important for practical reasons. But we can verify that only after we do all the complicated and fine-grained work on annotation, because this should be a baseline to which you compare your cheap annotation model. We're also starting to work on the influence of genres on referential choice. There has been a number of studies in the previous years showing that referential choice is sensitive to discourse type and genre, and our corpus is kind of balanced in terms of genres. It has 3 or 4 different text types, and according to our preliminary results, if you tune up your model to genre, you get little improvement. No, it's not dramatic, but it's there. Coming to my final conclusions, in this study we are implementing a multi-factor approach. We believe that referential choice depends on many things at a time, and you have to take many things into account to come up with a realistic model. We have a corpus large enough for machine learning modeling. results that we have so far are pretty close to theoretical maximum, and the rest, the remaining 10 or so % in the two-way task, can be accounted for only in a non-deterministic and non-categorical approach to referential choice. And more generally, I think that this kind of approach can be applied not just to this phenomenon, but to many other things in language production and language use. And thank you very much.
Proper science, you know, and mathematicians tell you it works, don't worry about that. So my question, of course, is more on the experimental side, which I understand much more about. Do you consider one of the follow-up studies where you could use a production task rather than sort of verification task that you use, or comprehension task, something like filling gap task or sentence completion task that could directly verify whether your intuitions or in fact whether your algorithm predictions are correct for sentence production? Thanks.
Well, thanks a lot for this question. It's a really useful one for me because we have already done that. We didn't have time to. I didn't have time to talk about that, and this is a kind of raw experiment. We haven't done all the analysis yet, but well, basically the design of that experiment was to give experimental participant a number of choices at a particular point in the text so that he or she would pick the appropriate ones. And we allow to pick more than one. And then compare the preferences or lack of preferences of average across the participants to what the different algorithms do. But we haven't processed all the data yet. We would be happy to discuss the details of this experiment with you if you like.
Hi, thanks for the talk. I'd like to know if it's a clarification question. So you have an algorithm which predicts the referent, right? The expression used for the referent. Yeah. Now, one of the things that, as far as I understand, that goes into this algorithm is a distance measure between the referent and the antecedent of this referent. Is this correct?
Exactly.
So what do you take as the antecedent is always what? Do you take morphology into the account? Is the morphological endings like S, which is identification of a referent, kind of mentions the referent again. Do you include that into your distance measure? Because the results might be different if you do. So the prediction algorithm might work slightly differently if you do.
Well, it's an exciting question. It's a really great question. I don't know how to move through this back to the... Yeah, maybe. Actually, I do believe that inflectional morphology is also referential. It's kind of more difficult to demonstrate it for English because this S, 99% of the time, occurs within a clause with an overt noun phrase, be it a pronoun or a full noun phrase. But in a language like Russian, it's not this way, and it's obviously, this kind of morphology is obviously referential. In the case of English, we have all kinds of zeros, so-called syntactic zeros, which come together with these ing forms, like here. And in these two clauses, actually there is reference to she in a way, and I didn't have time to say that, but as you ask, now I have time to say that in fact this referent referred to with she here and over there, it's also mentioned in all of these clauses through non-finite verb forms. And we are now working on our model, trying to tune it up so that you can compare modeling when you take that into account and when you don't. and see which way it works better. And the distances would be different. As I said, linear distance is 4 when you ignore it, and rhetorical distance is 1. But if you take that into account, then linear distance will be 1 and the rhetorical distance will be 2. So you can change this kind of little variables in the model and see what quantitative results it leads to. Yeah. Well, right now we still haven't extracted all useful information from this English language corpus, but when we are finished, maybe so, yeah.
Right, I'm afraid I have to stop with questions here to stay on time. Thank you again, Andrej, for an exciting presentation. And I would like to thank all the speakers of the first session. I think we've had a great start of this meeting, and for great talks and for staying on time. So please come back at 2 o'clock for the second session. And